introduce this subject on fire resistance steel structurals. And this is an iconic photo and symbolic too. And this sends a lot of messages. In fact, the important aspect is the sort of catastrophe that can happen in case of a fire. I think so. Mr. Gururaj mentioned about fire resistance steel structurals, availability of them and all. We're not going to deal with steel of this sort of catastrophe because this is a hydrocarbon categorized fire, which is very rare. But the normal fires that happen in buildings are normally cellulosic type, the office buildings, the composite structures or the furnitures, if they burn, then how would it impact the building? So, we today supply, as part of this Tata structurer, the YST 310 and the 355 grade of steels, which have these properties. But what is an add-on which we have recently developed and would like to introduce to this Tata structurer is the fire resistance aspect. And we are talking about fire resistance ratios, which is the ratio of the yield strength of the material at 600 degrees centigrade, in case of a fire, and at room temperature of greater than 0.50. Now, I'll tell you about the plain carbon steel and then get into the fire resistance development. Now, what is the implications? And this was expressed that you need to give 2 hours of evacuation time. See, when this fire happened, it was not that everyone in the building was killed. Many people fled this building. And the reason behind that is this building could sustain more than 2 hours before it collapsed. Now, how did that happen? Many of the soft aspects were discussed, and that was the media reports and all. But there was a lot of technological issues which saved many people's life. And even when the new building started coming up, there was a lot of discussions and debates on what new materials and steels need to be used. The Empire State Building, as he mentioned, has a lot of stainless steels, which is able to withstand fire, high temperature, has high temperature properties. But there are also many alloyed steels which have high temperature properties. But the issue with alloy steels and adopting to the Indian context is they're very expensive. So there are today two different solutions. One is the material solution, where you have a lot of alloy content in the steel, and the other is you put a paint coating, with a high fire rating. Now, the approach we went for is a material solution. The reason being, the paint perhaps is expensive. It has to be frequently applied, and there are other issues with paints also. And the availability is also an issue. So what we decided on, that we need to provide a low-cost solution to the fire-resistant steels. Now, if you look into the fire-resistance categories, there are different yield ratios which are used. Now, if you go to this sort of values of 0.66, then it becomes pretty expensive. And it is a rarity. And given this is abundantly used in Europe and Japan, the costs are high, and because of the sort of prefabricated structures they use, the structurals need to be of a high yield ratio. But there are also low yield ratio materials available. But the one we developed is really unique because it gives a cost advantage. Now, how does the fire resistant steel differ from the plain carbon steels or the normal steels that are available? That in case of a fire at 600 degrees centigrade, there's a bit of metallurgy, but it will be simple to understand. The yield strength falls. The yield ratio comes down to less than 0.3. And the yield strength is basically represented by this very famous Hall-Petch equation, where this is the frictional stress, and this is the pitch parameter, and this is the grain size. Steels have grains inside. Now, this is determined by the dislocations, how fluid the dislocations are inside. These are defects in any steel materials. Now, if you are able to inhibit movement of these dislocations, you can get very high yield strengths, and that is how the yield strength is maintained. Now, in case of plain carbon steels, the dislocation movement at high temperature becomes very fluid. Okay, it moves uninhibitedly, and therefore the grain sizes improve, and there is a fall in the yield strength, and therefore the yield ratio also comes down. Okay. Now, while going for a design of this steel, this is very standard composition with any of these YST 355 Tata structural steels. But the trick lies up here, where you need to use a judicious amount of microalloying element, okay, to see whether you would get the fire resistance properties. Now, the internationally available fire resistant steels, even there is an IS specification with the fire resistance properties, have extremely high microalloying elements, which makes it costly, and these are really costly materials. And so, to make it competitive, the challenge was how low we can keep this value, but still attain the sort of properties we are looking for in terms of yield strength. So, these are the considerations. This is the specification. The functional requirement was the temperature aspect. Cost from an Indian context is very important, and these are two internal issues, because even if we make a steel, it has to be manufactured in the steel plant. Perhaps the users look at steel as a commodity, but there's a lot of effort that goes into the design and manufacturing of steel, and the processing capabilities. Whether we could roll a tube of that strength, because if it necessitates a higher strength mill, then the cost implications would go up, and the supply prices would go up. So, it is very important that if we can use our existing mills to produce a tube which could cater to the larger community. So, this is something like the Intel inside. Any computer, you have the Intel inside. Similarly, in steels, which you don't see from outside, you look at it as a rusted material. It is particle inside. So, these are the different transmission electron microscopy photographs, and this is the very special concept design, where we have created this precipitates, and this precipitates, and this is a very smart steel. The intent was that as the temperature rises because of the fire to 600 degrees centigrade, these precipitates would evolve out of the matrix and retard dislocation movement and provide the necessary fire resistance properties. Okay, so with that sort of engineering, alloy design and engineering, we arrived at this sort of precipitates at high temperature, and confirmed by these, these are SAD patterns and X-ray diffractions to confirm the sort of precipitates we were looking for. And finally, we produced, commercially produced, not only lab, we produced more than 1,000 tons of this material, and has been supplied on a trial basis to various customers. This is just one of the rectangular sections that you see. We could have different sections of round and rectangular sections. The welds, which are basically, these are normally ERW processes, electric resistance welded tubes, and we did quite a good amount of quality assurance exercise to ensure that the welds were sound and the fire resistance could withstand the sort of structural requirements in the marketplace. So, and then these are some of the tests that we did to reinforce our thoughts of our findings. So this is at room temperature, the yield strength of this material. At 600 degrees centigrade, it drops, but it still is above this value. So it doesn't come to 0.3, but it remains above 0.5. So you are able to sustain the building, the structural collapse at that temperature. This is what happens, at different temperature slabs. Means, this is at 400 degrees centigrade, this is at 500, this is at 600. So, there's always this competition or, debate whether fire resistant paints is a good thing or a material solutions is a good thing. But, with this study, we have found that even if you put paint, it is not going to 100% retard heat transfer. Heat transfer is going to take place. In case of 600 degrees centigrade, the core would go up to 400 degrees centigrade. And how would the material behave at 400 degrees centigrade? So this figure says that the fire resistant plate would be able to sustain better heat resistant yield losses than the paint covered material. So this is again the YS UTS, which shows that it is up to the desired performance. This is in case of tubes. The earlier one you saw is for the materials that goes into the tubes, and this is for the tubes. The tubes properties were much better than 0.5. When we got figures, if you take the yield ratio, this is the yield strength. If you take the yield ratio, it is better than 0.6. That means it's got better, fire resistance properties than the base metal. We did some welding to see, because you need to fabricate the structures. It's not only the tube, and see whether the welds are able to sustain those sort of temperatures. Okay, so there are special electrodes. If you really require good fire resistant welds, then you can use those electrodes, but they become slightly expensive. But even if you use the normal the ones available in the market, they also give sufficiently good properties. These are some of the facilities in which we did the high temperature testing. These are the heating furnaces, extensometers, thermocouples, etc. We used to do this extensive tests we did before we really launched it in the market. We launched this product in the December 2015, officially launched it. So, just to summarize this part of the presentation is this is a lean chemistry precipitation strengthened steels. Therefore, you are able to keep the cost low. This complies to IS 10748, which is the BS material. Fire resistance ratio, as I said, is greater than 0.5, is formable and weldable. That means you are able to fabricate this material at the sites. And we got, apart from internal testings, we got it certified from NABL lab. And as Mr. Gururaj said in the morning, Mr. Hafiz, contractor in steel structures and metal buildings, January 2014, said this, that when it comes to final finishing, you have to do fire protection.
It's a famous saying from Winston Churchill, what I'm trying to say through this slide is art influences the way we think, the way the culture moves forward, or like how innovative we be. So it's quite important that we build structures which are inspiring people, which make people think just out of the box. And so I'd like to, and so this is a joke that I got from WhatsApp, and I thought I'd also share it with you. So that's like an architect starts off with a concept sketch which is like with grand and allure, and then by the time it keeps going through the circle of the construction process, it ends up becoming just simple box kind of a building and thing. So the main things that are hindering now are not the engineering. We are having a very good engineers right now in our country, and we have very good contractors in our country who be able to achieve whatever the engineer or the architect foresees in his thoughts. And so the things that are missing would be probably in the types of material that are available for the construction and the things that makes things beautiful. So there are still questions that are pending in this. So we are trying to address these questions. And so the products that we are having is we have introduced the 355 grade steel into the construction industry. And so which is giving you much more optimized structures than what we are having probably 3 years back. So this is a study which we did for a spinning mill in Surat, where we did save something like a 12% in weight and about 8% in savings in cost. So it's the kind of money that a person in the construction industry would probably give an arm and a leg to achieve such kind of a saving. So yes, we are being able to do that. So between the two grades of steel. And the next addition that we have in our portfolio of products is welded HNI sections. And we are entering this welded HNI section because we want to increase our range. The maximum square section that we make is a 250 by 250 square section or a 300 by 200 rectangular hollow section. So with this you can probably go till a 3-storied building only. And what is there when you go for much longer spans and for much taller buildings? And so then we have come up with this solution as making factory finished welded HNI sections. And the advantage over here is you can customize your elements, your structural elements, and you can optimize on that, and then you can start at element level optimization, and then you can think about how you can optimize the structure on a global level also. So so that's the greatest advantage that we see in this. And since we are making it in a controlled environment, we can achieve good high quality finishes in this particular range. So the range of sections that we can make is something like a 300 mm deep section to as deep as 2 meters with thicknesses from 6 to 40 mm. And we can offer that in a customized lengths also. So if at all we have an 8-meter beam repeating n number of times in a construction project, we would be able to optimize that particular element to whatever extent you want, and then we can repeat it n number of times. And so the questions, yes, it has answered. We are trying to answer these questions in terms of material cost and material performance through the 3 products that we are introducing to the structural steel market. Through the hollow section, fire resistant, and HNI sections. And thanks a lot for patiently hearing with us and with the Dr. Shome's speech also. And I'd like to end up with this particular slide. So this is a Firth and Forth Scotland bridge built in Scotland, and so I'd like to wanted to introduce this to you. Probably many of us would be aware of this particular project also. It's a UNESCO recognized project. It's a first steel construction of this particular big scale. About a 60,000 ton steel is being involved in this particular project, and it's a first steel construction that has been constructed in Europe. And the previous one was in Rotterdam, that's Eiffel Tower, and this is the second one. And here, this was again, this was a time when just a Bessemer process was just invented. It was just 15 years since the Bessemer process was invented, and the structural engineer, Sir Baker and Sir Fowler, both of them did a magnificent job in coming up with a structural system which uses a new material at that point of time, and brought up this particular change which revolutionized the steel construction. And I believe this is a kind of construction that influenced bridges like San Francisco Golden Gate Bridge and the Brooklyn bridges, and other steel construction also. So to me, this particular bridge plays a significant role in the construction way back in 1880. And so with this slide also, I'd like to encourage our engineers over here, so who have been already doing some fantastic stuff, coming up with good products and good structures. And so this can be actually seen in our coffee table book, which we'll be placing right in the desk. So some of the projects that we have executed in such, I don't want to cover it in these slides. So probably you can check it out in the book itself. So we are still encouraged. It's not about the scale of again, like what Mr. Sujay was saying. It's not about the scale of the project, but it's about what is a new thing that we are bringing in to the table, and from which you people keep building up and achieving greater heights. And I believe the products that we have introduced would help us in achieving that. And thanks a lot. Thanks for the time.